It's long been a goal of mine to properly learn 6502 assembly programming. I used to think that once I'd grasped it, I could make a few videos about the subject, but recently I had a thought. What if, instead of waiting, I just made the videos part of that learning process? Rather than learning 6502 from a master, you would be learning it alongside me, very much not a master, and we'll figure it out together. Most books on the subject of assembly programming do spend a lot of time up front on number representation, binary, hexadecimal, and how to do arithmetic in base 2, 10, 16, and so on. While I do personally find all of that very interesting, it's a little bit like being taught French by starting off with tenses, declensions, and conjugations, instead of learning how to introduce yourself or order a beer. Number theory, especially hexadecimal, is crucial to assembly programming, but it's not going to get you writing your first program in 6502. So in this series we're going to do things a little bit differently. First of all, we're going to be using 8-bit Acorn computers, the BBC Micro and the Acorn Electron, both of which have a 6502 CPU and run BBC Basic. Why does BBC Basic matter in a video about 6502 programming? Well, it supports something very powerful indeed, an inline assembler, which means that you can go into and out of 6502 assembly code directly from a BASIC program. Not only that, but BASIC can then interact with your 6502 code, making it much easier to write, edit and run. No need for a separate assembler program in ROM, as is the case with many other 8-bit machines. What's more, at a recent ABUG event, I was shown how to think in 6502 by imagining what it would be like to write programs in BASIC with a vastly reduced set of commands and variables. My thanks to Chris Bradburn for that idea, as it's really transformed how I think about 6502, and hence the name of this video series. So, with the introduction out of the way, let's dive in and get started. Well, it wouldn't be a programming tutorial if we didn't tackle the classic Hello World program. But instead of just showing you how to write it in 6502, we're going to begin by looking at how you would do it in BBC Basic. 10 print Hello World. So far, so basic. I mean, it's a single line, and it gets the job done quickly and easily. But what if we couldn't simply feed in that Hello World string to the print command directly? Imagine instead that print can only work with strings that have already been predefined. Well, in BASIC we could still do that, we just need to first define and then instantiate a simple string variable. If we change line 10 to text string equals hello world, and then have a line 20 that prints text string. Now imagine that we didn't have a print command. How could we still get a program that achieved the same outcome? Well, that's where it starts to get a bit trickier. I mean, if we haven't got a print command, how can we print anything to the screen? Enter stage left, the VDU command. This accepts a single byte and it prints it to the screen. So if I type VDU space 65, I get a capital letter A. Now there are two things to say about VDU. First of all, as you'll have noticed, we had to give it a number, but it printed a letter. And that's because VDU expects a byte, and bytes are numbers, not letters. However, inside the operating system ROM of the computer, in this case my Acorn Electron, there is an ASCII lookup that converts the numeric value to a corresponding display value. Indeed, you can check the numeric value of any ASCII character by using the ASC function. For example, if I type print ASC open brackets and then a capital A in quotes, it will return a value of 65, which is what we passed to the VDU command previously when we asked it to print the capital letter A. Indeed, you can achieve the conversion in the opposite direction using the CHR string function. For example, print CHR string brackets 65, and now we get a capital letter A. While most ASCII codes do correspond to displayable characters like letters, numbers, or punctuation marks, some are control characters, such as 10 for line feed and 13 for carriage return. Indeed, the combination of these two characters in sequence produces a new line. So, armed with our VDU command, we can now produce a basic Hello World program without needing print, right? Let's try it. 10 text string equals hello world as before, and then in line 20 we'll do a VDU text string. Not quite. So that type mismatch error tells us that VDU is not happy with being given a string because it's expecting a number. Fine, so let's wrap our variable in the ASC function. So we'll put VDU ASC brackets text string instead. Well, this is better, but it's still not right. All it's given us is the first letter of Hello World because VDU can only work with a single byte at a time. So it's taken the first one from our text string variable, and that's it. If we want to produce a Hello World output on screen with VDU, we're going to need to pass it 1 byte at a time in sequence. Now in BASIC, we can do that using a simple for loop, based on the length of our string. We'll also use the midString function to get the specific character of the string on each iteration of the loop. This is sometimes known as a substring function. Here, what we're doing is taking one character at a time by using the x% of our for loop to move through the string, with a fixed character length value of 1 each time to take just one character. Wrapping this inside the ASC function means that VDU gets the numeric byte value of the character. To make this more accurately mirror how the basic print command works, we should also put a new line at the end. We'll do this by concatenating a new line variable made up of the two ASCII codes 10 and 13 onto the end of our string. We can define this as its own new line string variable, or NL string, and then add this on to the end of tstring. And there we have it, we've achieved a Hello World program in BASIC that prints without using the print command. Except, to do that, we've introduced another feature of BASIC, namely the for loop. What if we wanted to still get the same outcome, but without using a for loop? And before you suggest it, no, we can't just use a repeat until loop either. That's cheating. Well, when you boil it down, a for loop is really a more concise version of an if-else conditional. On each iteration of the loop, my acorn electron is checking if x% has reached the value of the total length of our Hello World string. If it hasn't, it runs the VDU command inside the loop, and if it has, it exits the loop. So we could reconstruct this loop using an if, along with that most cursed of basic commands, the goto. We've still got our x% variable acting as our iterator, but it's now totally independent of any kind of for loop, so we have to increment it each time we step through the string. Instead of our loop managing the exit condition, we've also got to do this ourselves using the if statement in line 60. If our x% variable is less than the length of our string, it means we've not yet finished working through each character, and so we have to go to line 40 and repeat. Technically, we've implemented a repeat until loop rather than a for loop, because our program always calls VDU at least once before checking if we've met the exit condition. But the point remains, we have managed to construct a loop without using a loop. We've built it ourselves. And so we've managed to achieve a Hello World program in BASIC without using either the print command or either of BASIC's native loop structures. But hang on a minute, we're about 8 minutes into a video that's supposed to be about 6502 assembly programming, and all we've done is write a program in BASIC in a rather more tortured way than we would need to do if we were just going to write Hello World using BASIC. Well, that's kind of the point, because the good news is you've now taken your first step in thinking in 6502, because this version of the BASIC program, torturous though it is, closely parallels how the equivalent code would be written in assembly. 6502 assembly programming really is like writing BASIC, but with just 3 single byte variables, we can call these A, X and Y, and every operation, no matter how complex, has to be done 1 byte at a time. What is more, there are no loops, you must roll your own, as we have done here in BASIC. What then would a Hello World program look like in 6502 assembly? Before we can get to that, we'll need to take a quick look at how to write assembly code in line with BBC Basic, as that's the fastest way to get going with assembly programming on an Acorn machine, and that's what these videos are all about. Writing 6502 assembly code in line with BBC Basic has a lot of advantages, but the main one is being able to write and test your code directly from the BASIC prompt. To do that, however, you do have to tell BASIC that you want to reserve some memory to put your assembly code into. All the while you write in BASIC, BASIC will handle memory management for you. But when you step into the inline assembler, you now need to tell it where to find this code. To do that, you reserve however many bytes you think you'll need using the dim command. And it's really as easy as writing dim and then the name of your variable, and in this case we're going to use 255. What we're doing here is saying that we want to reserve 256 bytes of memory, and that those 256 bytes can be identified using the name of our variable, in this case mem%. Note, we use 255 in the dim statement, but we're reserving 256 bytes because the first byte is identified by 0, not 1. We say that it indexes from 0. That makes 255 the 256th byte of our reserved memory chunk. At the point where I want to step into the inline assembler, I just need to let BASIC know that it should set the program counter to the same value as mem%, which is really just another way of saying, wherever the program counter got to while working its way through my BASIC program, now go and point to the location where my assembly code will be found. And we can do this with a simple p% equals mem%. If you're not sure what a program counter is, think of it like a post-it note that BASIC uses to determine where to find the next instruction. Usually it handles this by itself, but when we switch over to inline assembly code, it becomes our job to update that post-it note's position. Now we're ready to step into the inline assembler itself, which we do by opening some square brackets and typing the OPT or opt directive, followed by a number. The number simply indicates what mode we want to run the inline assembler in, either reporting errors or not, and/or displaying the assembled machine code. While developing our code, I find it's best to use opt with option 3, since this will both report any errors and also display the machine code produced by our assembly code. Useful for debugging and confirming that the code really is doing what we expect it to. Don't get too hung up on this if it's not making a lot of sense though. You can think of this as just the entry requirement stuff you have to do to enter the inline assembler. For now, you can just copy the same approach every time. These 3 lines of code in BASIC are all you need to get into the inline assembler, assuming that you're not going to write assembly code with more than 256 bytes, which at this stage we definitely won't be. So now we're inside the assembler, but, well, what are we going to do next? We're in a different world. The commands here are not the same as they are in BASIC, but as you'll see, they do behave in a similar way to our BASIC program from earlier. Each of our 3 variables, or what we should properly call registers, A, X and Y, have their own commands to control them. If we want to set them to a value, we use LDA for A, LDX for X, and LDY for Y. The A register, which is also known as the accumulator, hence A, can have another numeric byte value added to or subtracted from it. In the case of X and Y, which are known as the index registers, we can only increment or decrement them by 1, using respectively INX and INY to increment, or DEX and DEY to decrement. Remember, these 3 registers can hold only a single numeric byte, so manipulating them likewise means doing so arithmetically. So let's do something very simple. All we're going to do is put a value of 65 into A, the accumulator. So I can do this by adding an extra line underneath my first 3 lines. I'm going to say LDA hash 65. The hash symbol here is being used to tell the assembler that the value we're passing to it is an immediate value, rather than a memory address that might contain a value. In short, we want the number 65 itself to be loaded into the accumulator, not some value that might reside at memory address 65. To exit the inline assembler and return back to BASIC, we need to use the RTS, or return to subroutine directive, followed by a colon, and then close the square bracket that we opened previously. Again, if any of this feels a bit mystical, don't worry too much about it for now. This is just how you exit the inline assembler and go back to BASIC. We can now run this program, and because we've chosen option 3 for our opt directive, we get a nice printout of the assembled machine code. At this point, we don't need to get too concerned with what these machine code values mean. Just understand that the number in the leftmost column is the memory address, storing our assembled 6502 machine code, and that the bytes in the middle correspond to the instructions in the rightmost column. As we become more and more familiar with 6502 coding, these bytes will likewise become more familiar as well. For now, we can just count the bytes and see that our tiny assembler program occupies just 3 bytes. A9, 41, and 60. Those are in hexadecimal, FYI. The bad news is that although our assembly code has been assembled without any errors, it doesn't actually do anything visible. It's the basic equivalent of running this basic program. A% equals 65. I mean, yes, it will run, but it doesn't do anything that we can see. It's instantiated a value, but we haven't done anything with that value. To bring this to life a little bit and get us closer to our Hello World program, we need to get the assembly code to call the equivalent of our VDU command from earlier. As it happens, the very same operating system subroutine that powers the VDU command is accessible to us inside the inline assembler. It takes whatever value is currently loaded into the accumulator and prints it to the screen. This subroutine is more properly known as OSRICH, or OS Write Character, and it exists at memory address FFEE. We can thus add an extra line to our assembly code as follows. Now, the JSR opcode means jump to subroutine, hence JSR, and we have to follow it up with a memory address where said subroutine can be found. So of course we need to make sure that there actually is a subroutine at that address, otherwise it won't work. Now the ampersand prefix, by the way, means that this value is written in hexadecimal. I could have written it in conventional decimal by saying JSR 65518, which is the same memory address location but in decimal. However, the more assembly coding you do, the easier and more convenient you'll find hexadecimal, even if only because it requires fewer keystrokes. Now we can try it out both ways, and each time you can see that the assembler produces exactly the same machine code output. So the number 65518 in decimal and the hexadecimal value of FFEE are exactly the same as far as my Acorn Electron is concerned. You're probably wondering though why the program still doesn't do anything visible. And that's because all we've done up to this point is define a subroutine in 6502 assembly. We've not actually called it yet. That's easy enough to fix. We just need to tell BASIC to call the memory address of our code. And as you know, mem% is where we're storing our code, so if I call mem%, as if by magic, a capital letter A appears on screen. We're a lot closer now to our Hello World program than you might think. All that remains is to provide our assembly code subroutine with the necessary string and then construct a loop using one of our index registers. Let's start by defining the string, as this will get us onto the important topic of labels. To reference a section of code in 6502 assembly, you don't use line numbers as you do in BASIC, but rather labels. And once you get used to them, they're vastly more flexible, not to mention more human readable. They're essentially the 6502 assembly equivalent of line numbers in BBC Basic, but more descriptive. Or at least as descriptive as you choose to make them. In our program we need some text, and so we'll label the section of our code where the string is to be defined as .text. Now following .text we use the equus, or equate string command, which is a handy addition from Basic 2 that allows us to define strings inside assembly code. It does nothing more than poke the individual bytes of the Hello World string into consecutive memory addresses. If we run the code now, you'll see this in the machine code output. That cluster of 13 bytes directly after the .text label corresponds to each of the characters that make up our Hello World string in hexadecimal. One other thing you'll have noticed is that we have a slightly odd error message, blank at line 600. Now the reason that we're seeing this is because we've told BASIC that at line 600 you should call our assembly code using mem%, but whereas previously the first byte at the start of mem% was the 6502 instruction LDA, we've now stuffed in some ASCII character bytes instead, the first being 48. Now for us that means capital letter H. And so you might be thinking, as I initially did, well, that's not an instruction at all, and that's why we've got the error. But actually there's something slightly more subtle going on here. And this is quite an important thing to emphasize. The 6502 has interpreted those bytes as instructions. 48 turns out to be one of them, as do several further bytes, one of which tells the 6502 to go looking at an uninitialized memory location totally unconnected to our program. Now, what it will find there is really anyone's guess, but it certainly won't be what we want. In this case, it looks like it's probably found a 00 byte, which is understood as break, but without any follow-on byte indicating the specific error code, hence our slightly cryptic error message. All that we're able to say here is that an error has occurred. Now, believe it or not, we've actually been really lucky. BASIC has managed to catch the exception and our program has errored gracefully, albeit with a slightly odd error message. Now, depending on what else it might have found in that uninitialized memory address, the 6502 could have gone on running instruction after instruction for as long as it could find consecutive bytes that meant something to it. This can lead to chaotic, possibly even destructive results, which could include overwriting or corrupting the code of our own program. All of this is to say that when you're in assembly world, what you might intend as data, the 6502 may very well interpret as instructions, just not the ones you wanted. And so you should always take great care with precisely which memory address you start your subroutine call from. Now, we can fix this problem of unintended instructions by adding a second label directly under our ECUS line and tell BASIC to call our subroutine from that label. So at line 330 we have a dot start, and then at line 600 instead of call mem%, we have call start. Notice, by the way, that labels are defined with a leading full stop or period if you're American, but they are referenced without the leading full stop. This is the same whether you are referencing them in assembly code or in BASIC. Now, our string is safely defined in the assembly code, but the first instruction that BASIC will encounter when it calls our subroutine from the start label is the LDA instruction, which is what we wanted. Accessing the string is similarly easy now that we have a label for it. What happens if we rewrite line 400 as LDA text? Here, text is acting as a memory address location, and so we get the letter H printed to screen, except this time it's doing so by taking the first byte of our string. To get our code to print the remaining characters, however, we're going to need to build a loop, just as we did in BASIC. In 6502 assembly, we can load values into the accumulator from a memory location offset by the X or Y registers. If we add LDX #1 and then rewrite line 400 as LDA text, X, we now get the letter E printed instead. Clever, eh? This gives us a hint as to what we need to do to construct our loop. X, as you will recall, can only be set to a particular value and then incremented or decremented by 1. So let's start by setting it to 0, LDX #0. This means the first time we execute line 400, it will load the accumulator with the first byte, designated by our text label memory address, because it's being offset by 0, or nothing, which means that the first byte at that memory location will be the one that gets selected, the capital letter H. Before we can think about how we manage incrementing X, however, we need to consider our exit condition for this loop that we're building. What is going to indicate that we've finished reading from the string? In BASIC, we used the len function and drove our loop on the basis of the string's length, but we don't have that luxury available to us in 6502 world. Instead, we're going to need to base it on the byte in the accumulator on each iteration. Now, we could be lazy and define our exit loop condition as when accumulator contains the byte corresponding to the exclamation mark. But what if our string contains more than one exclamation mark? Maybe it's a very excitable Hello World program. Well, it's safer then to use a control character, such as character 10, known as the line feed. Since it isn't a printable character, we'll need to load it into memory at the end of our string using equb, which stands for equate byte, just as ECUS stands for equate string. So we can add an extra line, equb10. As it comes directly after our ECUS command, the next consecutive byte after the final byte of our Hello World string will be the line feed, and we can now use this as the thing to check for. But how do we do that? Well, in 6502 we have an opcode called CMP, or compare, and this compares the value in the accumulator with the value that you give to it. You can then use either the BEQ, or branch equal opcode, to branch to a particular label if the values are equal, or BNE, branch not equal, to branch to a different label if the values are unequal. It's just like the if-else conditional logic we might use in BASIC. In our code, we want to keep incrementing x and calling our osrich subroutine until the value in the accumulator matches 10, at which point we want to stop. To do this, we're going to need an extra label, which I'm going to call startPrint, to designate the start of the loop that we're going to create. I can't just recycle my existing start label, of course, because that means that we'd be constantly resetting x to 0, and thus our loop will just keep printing the letter h forever. Just as we've incremented x% in our basic program, we'll do the same thing here, but using the inx, or inx, directly after calling the osrich subroutine. So line 460, inx. Now we can add in our compare #10 command to check if the value that we've loaded into the accumulator at line 400 equals 10. So that's just cmp space #10. If it isn't equal, we want to keep iterating, and so we'll use the BNE, or branch not equal, and send that back to the startPrint label. This will go back up to line 400, but since we've already incremented x in the previous iteration, it's going to pick and print the next character in the string. Our loop will keep doing this until the value in the accumulator equals 10. At this point, the branch condition at line 480 will not be met, and we're going to exit our loop. This takes us to the RTS opcode, and we're back in BASIC once more with our Hello World message printed. It does look slightly odd because of that line feed character that we appended to the end, but this is easily fixable. We can append an extra ECUB with a carriage return character, or ASCII code 13, and use that in our CMP operation instead. Now our logic is testing for character 13 instead of character 10, and as you'll recall from earlier, the combinations of characters 10 and 13 produce a new line, which is exactly how the basic print command works. Is this the most elegant and efficient assembly code ever written? Probably not, and I've deliberately written it in a way that avoids forward-looking labels, because that takes us into slightly trickier terrain when working with the inline assembler. But does it achieve a Hello World program in 6502 assembly code using a method that we pioneered in our basic program after stripping it of its native loop structures? I think it does. This may have felt like a very lengthy way of getting to a Hello World program, and there are plenty of tutorials and videos out there which would have probably got the point across much faster. But my goal here was to take you through the thought process that results in a subroutine like this one. Thinking in 6502 takes a different mindset, particularly if you're anything like me and you're used to writing software in higher level languages. But the fundamentals of assembly coding are still there and can be replicated in those languages, just like we've done here with our BBC Basic program at the start of this video. Well, I hope that you found this useful, and really do please let me know in the comments if you'd like to see more videos like this in the future. I'm going to say thank you again to Chris for his help in getting me to think in 6502, as well as for collaborating with me on this video. But we're all human after all, so if you do spot any errors or feel that there are points that should be clarified in future videos, don't hold back. I do love reading comments, as I always say. For now though, I'm just going to say thank you for your patience if you've made it this far, and until the next time, goodbye.